everybody, and welcome to Echo Live. My name is Anna, coming to you from the Michigan Science Center's Echo Distance Learning Program. Today I am back here with my funny hat and with an additional piece of scientific apparel, because today we are going to talk all about fossils and excavation and things of that nature. Now I see some friends starting to tune in already in Facebook and YouTube and right here in Zoom, where our meetings are streamed out from. If you haven't done so already, go ahead, introduce yourself in the chat feature of whichever program you are tuning in on. I'd love to hear from some of our familiar friends who tune into Echo Live just about every day. If you are new here, you can go ahead and you can use the chat to tell us who you are, maybe where you're watching from, and that chat feature will be your way of communicating with me throughout my program. Now, I've got another game for us to play today. Since we are talking about fossils, I thought we could play a bit of a guessing game to kind of kick off our activities and our lessons here today. Now, before I give you any background knowledge, I thought it might be fun to do kind of a fun pop quiz. Now, remember, we're all just working off of our own opinions and our own prior knowledge. So as we play our game, which is called Which is a Fossil, it's okay to make a guess. I'd love to hear your feedback. It helps me enjoy the programs when I see people chiming in the chat feature, helping to answer some of these questions. That way I know I'm not just here talking to myself. Now, I will admittedly say that I am no expert in fossils. I am no expert in archaeology, paleontology, but the best part about teaching Echo Live and facilitating programs is that I get to learn a little bit every single week about a new topic. And so I've learned a little bit about fossils before this program. I'm hoping to share some of the things that I found most interesting with you. Now let's go ahead and we'll kick off our game. Now the object of this game is just that you are going to tell me which of these two objects is a fossil. So we've got our first which is a fossil slide up here on the screen now. And I want you to tell me, in your opinion, or based on what you might know about fossils or what you might know about ancient artifacts, things like that, which of these two objects is a fossil? Is it an agate geode? We might remember these from an episode of Echo Live where we talked about crystallization. Or is it a Petoskey stone? If you are a Michigan native, like I am, you might be familiar with Petoskey stones. If you are from outside of Michigan, perhaps you've heard of these, but here in Michigan, we actually find these washing up on the shores all the time, which is why we refer to them as Petoskey stones, because they are especially prevalent in an area of Michigan called Petoskey. So tell me in the chat, is it the agate geode or the Petoskey stone that is a fossil? I'm interested to hear what you think and what you might know about either of these two objects. Let's see, Elizabeth said the Petoskey stone is the fossil of these two objects right here. Let's see if we've got any friends. No one answered yet in YouTube. Let's see. Theo said it's the Petoskey stone. All right, so a couple votes coming from Theo and Elizabeth's house. Very cool. You are exactly correct. The agate geode is not a fossil. This is an example of a crystal. Now, this brings us to an important question, right? What makes a fossil? Because we might consider both of these to be minerals or stones or rocks or things like that. But the big difference is that an agate geode was never alive. And you might be thinking to yourself, well, wait a minute, was a Petoskey stone alive? And actually, it was. A very long time ago, Michigan, and especially our entire region, was actually covered in a shallow tropical sea. And in a tropical sea, of course, we have coral. What Petoskey stones actually are ancient remains of fossilized coral. And so since a Petoskey stone was once a living thing, the Petoskey stone is the answer to our first round of which is a fossil. Good job, everyone at home. Ooh, Evan said so as well. Oh, Evan even knew that it was coral ahead of time. Awesome. All right, next round of which is a fossil. Is it the dendritic mineral growth, which is this photo over here on the left, or is it the Cretaceous leaf? So think about that. They look very similar. These might be perhaps formed in similar ways, but only one of these is actually a fossil. If we're confused by some of these words, dendritic refers to this pattern of the mineral growth that's here on the rock. Dendrites are those connections inside your brain, and usually they have all these sorts of crazy little finger-like or branch-like structures coming off them. So dendritic just describes the shape of this mineral growth, and Cretaceous is just a period in time from here on Earth. Which of these two is the fossil? Again, there's only one answer to this question. Which is a fossil? Is it the dendritic mineral growth, or is it the Cretaceous leaf? Take a moment to think about it if you need to. Think about what we know so far, or use your prior knowledge about fossils. Only one of these objects is a true fossil. And Theo tells us again that the Cretaceous leaf, and so does Kelly, the Cretaceous leaf is absolutely the answer. If we think back to what I said in our first slide, right, these things, fossils, have to be either a living thing or evidence of a living thing from long ago. So the Cretaceous leaf is absolutely the answer because trees are living things. Fossils are not just from animals. Fossils can be from any sort of life on Earth, whether that's plants or bacteria or anything that is truly alive. Dendritic mineral growth looks a lot like a plant, but that's actually why I labeled these pictures, because minerals or crystals can actually grow in these crazy shapes as well that might fool you into thinking that this was once a plant or another type of living creature, but this was in fact just minerals that were kind of imprinted on the surface of this rock. And so this one is not a true fossil, even though it might be just as old and just as cool to look at. Let's try a couple more. Between these two options here, which is a fossil? Is it the permineralized wood, or what we might also call petrified wood, or is it these desiccation cracks? Tell me what you think. If you are not sure what a desiccation crack is, these you might see in the desert when an area goes a very long period of time without rain. The ground will actually start to crack. I can actually change my virtual background here. Tell me in the chat, as I change my virtual background, tell me which of these two options is an example of a fossil. Is it the permineralized wood or the desiccation cracks? Wow, I'm going to keep saying that wrong. Again, if you're looking for what a desiccation crack might have looked like long ago, or before that kind of rock formed, this is what it might look like. And I'm sure if you've seen images of the desert before, or of really, really dry environments here on Earth, you might be familiar with these, or at least have seen them before. So go ahead, tell me in the chat which one is the fossil. Awesome, everybody. Right again, everyone is voting for the wood, probably because we know wood was once alive, right? Now, even though of these two images, the wood may not look as old or may not look as much like a fossil as we might traditionally think of one, the desiccation crack doesn't provide proof of life. Now, that doesn't mean it's not old, and it doesn't mean that it's not important for scientists learning about the history of Earth long before the time of humans. It truly is. But again, the definition of a fossil is that it provides evidence of life. And so these desiccation cracks, they look like a fossil. They're formed by a very similar process, but the ground is not alive. The dirt is not alive. Things inside the dirt could be alive. So this one is not truly a fossil. All right, last one. And this one is my favorite one. Of these two, which is a fossil? Is it the Egyptian dental work? And so this was discovered from an area in Egypt, and it's dated to be from the 17th century BC. So a very long time ago, certainly. And you can see that even the ancient Egyptians knew how to do dental work, which is very important, and it helped them to shape their society, right? Keeping people's mouths healthy for longer, helped them to improve their quality of life. So that's option A, the Egyptian dental work, or is it the coprolite? And coprolite is just a fancy scientific name for dinosaur poop. So I wrote dinosaur dung. That way no one can look back on this PowerPoint later and see the word poop. But it really is. It's just dinosaur poop. So very, very old as well. Now, which of these is a fossil? Think about that. Think about what we've known so far. And tell me in the chat, which do you consider to be a fossil? Or which do you think is the fossil by the true definition? Let's see, Lyle in YouTube has gotten them correct so far as well. Tell me what you think. Is it the Egyptian dental work or the coprolite? Give you all just a moment to weigh in. Love to take a couple votes on this one, since this is my favorite round of this game. Now, in addition to a fossil having to represent something that was once alive or providing evidence of something that was once alive, there is another criteria that you have to meet in order to consider something a true fossil. And Theo knows exactly why. Theo says that even though they both come from life, right? So certainly humans are living creatures. And so evidence of this skull, right, is definitely proof or evidence of life, but so is dinosaur dung. Dinosaur dung also provides us with evidence of what life was once like or what life might have looked like on Earth long ago. But Theo tells us that the dental work is not technically old enough. It does matter how old one of these fossils is. To be considered a true fossil, the general rule of thumb in the scientific community is that a fossil has to be at least 10,000 years old. So the 17th century BC isn't quite old enough. So this dental work, not quite 10,000 years old, even though it is very, very old, right? If it's from 17th century BC, so think about what year we're in now, that many years plus or 1700 more still doesn't quite get us to 10,000 years from this date. But dinosaurs walked the earth hundreds of millions of years ago. And so the coprolite is in fact fossilized dinosaur dung. So there are two main criteria that you have to meet to be considered a fossil. Number one represents life. Number two, the age of the fossil itself. Now, there are 5 main types of fossils, and we classify them in a few different ways. Number one, we have what we call carbon films. So if you think back to our Cretaceous leaf, that Cretaceous leaf was a carbon film. Sometimes when a living organism, when it dies and it's laid on top of a hard surface like a rock or a stone, over very long periods of time, sometimes all of the minerals disappear except for carbon. And when only the carbon is left behind, it leaves us with almost what looks like a photograph of that living organism. So you can see this is another type of fossilized leaf, or a carbon film of a fossilized leaf on top of the surface of a stone. And these are actually incredibly common. If you ever walk the beach, keep your eyes out because you could find fossilized remains of plant life or aquatic life washing up on shore on top of the surfaces of certain rocks. We also have what we call molds and casts, or mold fossils and cast fossils. Now, when an organism dies and is buried underneath an immense amount of rock and the rock around it hardens, sometimes that organism will disappear, leaving behind an empty shell. We call that a mold. Just like you might have made ice cubes in an ice tray before, that's what we would consider to be the mold, the empty space that's left behind. But the cast would be the frozen ice inside. And so over time, that empty space can get filled with other substances. Minerals that seep through the earth can actually fill in the mold and almost fill it in like a Play-Doh mold or like an ice mold or a candy mold. And we call that a cast fossil, even though what's inside the mold isn't necessarily the living organism itself. It is a good representation of what it looked like, or at least its exterior shape or structure. We also have petrified fossils, like the example that I showed you earlier of the petrified or permineralized wood. Permineralized means that over time, this entire organism was actually, its structure was replaced by different types of minerals. And so it leaves us, again, almost like a cast fossil, it leaves us with an exact replica of that shape that the minerals filled in and actually replaced that fossil bit by bit by bit with petrified or permineralized minerals. There's also what we call trace fossils. Now, trace fossils are an interesting one because so far what we've talked about is the actual living organism itself, either a plant or an animal or a part of an animal like a skull or a tooth, right? Those are different types of fossils than trace fossils. Trace fossils only provide us evidence of life without being the life form itself. So a footprint is a fantastic example of a trace fossil. They're formed in very similar ways, right? They're over long periods of time, millions of years even. The minerals can harden, be compressed underneath different layers of rock. Over time, they are exposed so that humans can find them. But these trace fossils provide evidence of what life was like or how these different living things behaved. So trace fossils could show us things like how a dinosaur or organism moved. It can help us to show how big it is. Did they travel in herds or were they solitary? So trace fossils, even though it's not the living organism itself, can actually tell us even more sometimes about a living organism or its lifestyle than just finding the actual entire organism. Now, the last type of fossil are preserved remains. And you might know a pretty famous example of preserved remains, even though this is a fictional example. If you've ever seen the movie Jurassic Park, a mosquito that lived in the time of dinosaurs was actually trapped or encased in a layer of amber, which is ancient tree sap. Since that organism is entirely preserved, its entire body, all of its insides are encapsulated in that amber, it's entirely intact. And so that's an example of preserved remains. If you've seen this movie, it's awesome. There is a little bit of science fact to it, even though most of it I would call science fiction. But, you know, that movie's pretty old, and they did a pretty good job of showing us what the possibility and importance of studying fossils really is. Now, of course, I have some examples of fossils up here on my distance learning table. So I've got some fossils from our collection. Some of these are real fossils, and some of them are either replicas or molds. And all of them have a scientific purpose. All of them are important. So let's go ahead and look at a couple of them that I have here on the table. This is a great example of what type of fossil. It's one of the types that we just mentioned. So that this one is super important. Now, clearly, this is not an entire living organism, right? This is a different type of fossil. So it's certainly not preserved remains. It's not an entire organism that's been perfectly preserved since its lifetime. I will say that this one is also what we would call a replica. So this is not a real fossil that was dug up outside, but this is a replica of a certain type of fossil. And can anyone tell me what type of fossil is this? And while you tell me what this is, I'll tell you the organism that this is giving us evidence of. So this is from a meat-eating dinosaur, generally classified as a, oops, I'm going to say it wrong. Okay, it's like Cayennetipus Minor, which generally we would call a theropod, meaning that it ate meat and that it lived in, this one actually lived over 210 million years ago in Virginia. This is an example of a trace fossil, right? So a trace fossil provides us evidence of this animal's movement or environment. And so this is a footprint, right? So this is an example of a trace fossil, not the organism itself, but this could tell us exactly how much the dinosaur might have weighed. If we found multiple footprints, we could tell how fast it could run, or how long its stride was, which could help us to figure out how large this animal was if we don't actually have the organism itself. So this is an example of a trace fossil, but I have got a couple other types of fossils up here too. We have an example of a trilobite, and this is a real fossil. So this is a real fossil. Let's zoom in, because this one's a bit smaller. A trilobite is very similar to what might look like our Madagascar hissing cockroaches that we've shown on a previous episode of Echo Live. But these were aquatic organisms. We can actually find ancient or descendants of these organisms even today. But this, we can actually see just the imprint that's left behind, which means that this type of fossil is what we would call a mold fossil. So it's just empty space that was left behind. We can see what this organism would have looked like from the outside, but the organism itself is not here. So it's not a preserved remains. And so this one is a mold fossil, or yes, a mold fossil. Now, we've got some other examples here. This one, for example, this large one is another replica, but this is what would represent a trait or a cast fossil. So this has been filled in over time. And so this is a replica or a cast fossil that they actually filled in so that we could look at these right here, which are called Ammonites. And Ammonites are another aquatic species that lived hundreds of millions of years ago. And what we notice is that, right, even though we do most of our excavation on land, most of the biodiversity on Earth is located in the ocean. Now, it's a lot harder, right, for us to excavate the ocean because it's underwater. But if we can think about all the biodiversity that we've uncovered on land, such as T-Rex and other sorts of land-dwelling dinosaurs, imagine the type of fossils that must be buried deep below the surface of our ocean. We may never, in our lifetime at least, get to find out even a fraction of the biodiversity that lived underwater. Things like these Ammonites, which lived hundreds of millions of years ago as well. Now, we talked about one type of fossil that you might find outside if you live here in Michigan, something like those Petoskey stones, which I showed you a picture of earlier. But if maybe you live somewhere closer to the ocean, you might find instead something like this. Now, this is certainly not a Petoskey stone. This is more commonly referred to as a sand dollar, but this is in fact a fossilized remains of an ancient ocean-dwelling creature as well. And so these you would only find near the current ocean. Unfortunately, they're not so common in Michigan because this exact species of aquatic organism probably didn't live in this part of the Earth. Now, let's see, I had a question come in the chat. Let's see, do scientists look through dinosaur dung to find bones? And they absolutely do. Just like we actually look through dung from animals that are alive today to help teach us about their diet, we absolutely look through dinosaur dung to try to find fossilized remains inside them as well. Now, we don't always, because over time it's become fossilized and it's very, very hard. And sometimes the goal is just to preserve that dung itself because it can help us to tell us about the size of the animal. But we also do excavations inside the coprolite or the dinosaur dung to figure out what they might have eaten. Now, of course, anything inside the dung, right, is also hundreds of millions of years old. And so it's not likely that we would find anything that is still living inside them, or at least we haven't so far. But it is possible to still learn from other things that might be inside there, like additional fossilized bones or other types of smaller fossils that live in or that were eaten by the dinosaur whose dung that we are excavating. Yeah, let's see. Oh yeah, Evan knew this was a sand dollar. I know Evan lives in Texas, so perhaps quite a bit closer to the ocean than at least where I live. All right, I've got two last fossils I want to show off that I have here from our collection. And then I've got an activity that you can all try at home to practice some of your paleontology skills. Now I've got two what we would call cast fossils here, but these are molded from the shape of a fossil that we had found. And both of these are actually teeth, but they look pretty different, very similar in size. So if you could imagine the size of the creature that this tooth must have come from, both of these are molars. And so if you were to look at your own molars in the mirror, you might notice some similarities or differences between our molars and these molars. Perhaps if you've ever lost a tooth and gotten to look at the entire structure, like the root, you might be able to see even more similarities. Now, both of the organisms that gave us these two teeth actually lived in Michigan, but definitely not in our lifetime. a very, very long time ago during our last ice age. So both of these teeth come from a big hairy creature. One of them comes from a mastodon, and one of them comes from a mammoth. So if you've seen Ice Age, the movie, you might know that there is a big woolly mammoth in that movie. Now, mastodons and mammoths are very similar types of creatures when we look at their external structures, but since we never lived at the same time as these woolly mammoths or mastodons, we don't know a whole lot about how they behaved. But fossils, like these teeth, can actually tell us things that we can't observe now that those animals have gone extinct. Now, if you look at the two different kinds of teeth, that might be able to tell us, right, that even though these are both molars, they clearly ate different kinds of food. Now, the mastodon has these very pointy molars with almost like conical shaped structures coming off of them. This tells us that they had to do a lot more chewing and grinding of their food. And so what we've discovered through studying fossils and other sorts of ancient artifacts from that time frame is that mastodons actually ate more tree-like structures, whereas mammoths were grazers. And so mammoths grazed the ground, and they actually just did more grinding of their food. And so the shape of their teeth can help us to determine what direction they chewed. So whereas mastodons might have had more of an up and down kind of chewing motion to kind of mash and break up their food, since they ate more wooded things. But mastodons, we can see that these flat structures would be more ideal for a back and forth kind of grinding of their food. So very, very flat, because they ate very, very different things. So again, another example of a animal adaptation, right? Even teeth or even the different sorts of structures of these animals can tell us about the life of these animals, even though we've never gotten to experience them live and up close. And until Jurassic Park comes true and we can maybe find some DNA evidence from these creatures, we're probably never going to get to see a woolly mammoth or a mastodon up close. Evan asked a really fantastic question in the chat, and I'd love to answer that one. Evan asked, what is the difference between archaeology and paleontology? And you might have noticed that I've said it a couple times, trying to use them in different contexts, because even though just like mammoths and mastodons, even though they're very similar, they also have their differences. Now, both archaeology and paleontology are studying ancient artifacts, trying to learn about what life was like before our written record of history. The difference is paleontologists specifically study fossils, whereas archaeologists are more interested in human life. And so archaeologists will study ancient human remains and human artifacts. So things like tools or pottery or structures. Archaeology is interested in not just life, but how civilization worked before we have written or detailed records. And so archaeology is human focused, whereas paleontology is focused on fossils, evidence of life. And so paleontology would technically include fossils of humans if we found some that were at least 10,000 years old. But technically paleontology is just an older science. They're more interested in the biodiversity of life before humans, whereas archaeology comes into play once humans started inhabiting Earth. Great question, because there is a pretty big difference between the two. Now, I've got two activities. One of them I started to set up, and I'm going to show you my progress so far, and then a fun one that you could try at home. I suppose you could try both of these at home. Now, what I did before the program is I started off this activity here. Let me turn off my virtual background because it's a little distracting, like always. This is an activity where you can make your own cast or mold and cast fossils using Play-Doh and white glue. So what I did before the program, or actually I did this yesterday, I actually just took some Play-Doh, or you could use modeling clay, and I just smashed it really, really flat and put it down here on my tray. I then took something, I chose to use some of these silicone animal prints. This is actually the footprint of a weasel, which is a native species to Michigan. And I just made an imprint down into the modeling clay or in the Play-Doh. What we've made right now, right, this, if we were to put it in the oven and preserve it, cause that Play-Doh to harden, this is what we would call a mold fossil. And you can definitely make these at home. But I thought I wanted to make a combination. So what I did is I took some white school glue and I actually poured it down inside our mold fossil so that I can make my own cast fossil. Once this glue dries completely, I'll be able to remove just the mold from inside, giving me a cast fossil. Now, I read online that it should take about 24 hours for white school glue to completely dry to form our fossils like I'm trying to make here. Unfortunately, you can see that even if I kind of wiggle it around, or if I were to touch it, you can see that it's still a bit tacky. And so it's not quite totally dry just yet. So I'm not going to try to remove my cast fossil. Unfortunately, 24 hours was not enough for the brand of school glue that I used. It could also have to do with the depth of my mold here. So maybe it's a little deeper than the one that they did online. And so I'm going to give it another couple days to try to fully harden. I will try my best to get these done by our Thursday Echo program so I can show you the results of this. But I also have another really fun activity, and I'm especially excited about this one because I'm not sure if anyone knows this, but today is also a very important holiday, or at least very important to me. Today is actually National Chocolate Chip Cookie Day. And it lined up perfectly for me because I actually have an excavation activity using a chocolate chip cookie. So if you didn't have enough reason already to celebrate National Chocolate Chip Cookie Day by going out and getting yourself one, I highly encourage you to go do that because you can actually use it for a very cool science activity. Now, this one is on our Michigan Science Center website. You can find it if you go to our at-home science page, which of course I will note in our last slide. If you just go to our website and look for at-home science, you will be able to find an activity guide complete with step-by-step instructions about how you can practice your excavation skills by trying to remove very carefully the chocolate chips from inside one of these cookies. Now, I always like to give some alternatives. So if you are not a cookie fan or maybe not allowed to have cookies, which is understandable, you could also try to excavate the chocolate chips from a granola bar. Or if you're not a chocolate chip person, perhaps you could try an oatmeal raisin cookie. But the goal here, right, is just to practice using some of these skills that scientists have to use in order to excavate or remove artifacts carefully from a dig site. And so this worksheet is listed on our website as well. So if you go to our website, you can find this activity guide, you can find this printout. And what we're going to do is we're going to trace our cookie and try our best not to move it. I know I already kind of bumped it here, but we're basically just going to draw ourselves a map just by tracing the perimeter of our cookie. You can remove it first, which might make it easier for you to replicate this down here. The grid will really help with this part of the activity because not only is it important for scientists to remove the artifacts, let's see, I think it starts here. It's important that they know where they came from because they want to know which fossils were found in a particular area. It's important to know exactly how many of those fossils were found together or were they found separately, because that can tell us not just what the organism looked like, but how it interacted with its environment. So we set up this grid, and of course you can start by drawing onto the grid B. You can start mapping some of those visible artifacts, which in this case are chocolate chips. And so you just try to line them up as best you can. So underneath this line 5 here, we've got a chocolate chip, got another chocolate chip, perhaps a smaller one right there. All right. So now that I've mapped most of the visible chocolate chips, right, this is when the excavation comes into play. You need to use very, very good excavation skills. So you can use something very small like a toothpick or maybe even a paintbrush would work fantastic for this. And your goal is to excavate the chocolate chips as carefully as possible. Now, what types of things are scientists looking for at dig sites? Can anyone tell me? What kinds of things are they looking for? Maybe if we think back to our definitions of paleontology and archaeology, right? You'll know that we could be looking for all sorts of things, whether it is fossilized remains of humans or of dinosaurs or of other living animals, or if it's pottery or tools. The most important thing on a job site or a dig site is that you don't damage the artifacts as you remove them from the ground. Now, of course, right, there could also be artifacts under the surface of our cookie, things we can't see from the top. And so you'll see by doing this yourself that excavation is a very, very patient and difficult process. You don't know what's under the surface, and so you have to kind of watch as you go to make sure that you don't damage the artifact you're aiming to remove, but also so you don't damage any artifacts that might be under the surface. And you can see that I already did not do a fantastic job because my chocolate chip left a little piece of it behind there. But of course, we want to take that chocolate chip, take it from grid A, and drop it down on grid B in our labeled location. And it might be a fun idea if you're going to try this at home to try to time yourself. Now, of course, you might be thinking to yourself, Anna is not really going to excavate this entire chocolate chip cookie here on the air. And you are absolutely right. I won't do that to you because you can see that it took me a couple minutes just to remove our first artifact, or chocolate chip. I highly recommend that you try this one at home because it's going to show you exactly how difficult this process is, but it can be very, very rewarding once you entirely reconstruct your grid. Now, scientists, like we said, they do this in real life too. It's not just something that we do here on Echo Live. Scientists really do map out a grid system to help them figure out what kinds of objects or artifacts or fossils they find in each of the locations that they are digging at. So this is an example from a dig site that's in Pennsylvania, where they set up their grid, and then scientists or archaeologists or paleontologists, whoever kind of scientists they might be, will actually dig in a specific square, and so they can map out the locations of anything that they might find. Now, if anyone has any questions before we head out, I know I'm a few minutes over. I only see you guys once a week now, so I just talk and talk and talk. It's so nice to see you all. If you have any questions about these activities or anything about what we've talked about so far, definitely type them in the chat while we wait for some questions to come in. Of course, a couple announcements. First and foremost, big thank you to the sponsors of Echo Live, like Ford and Denso, who allow us to bring these programs to you for free every week. We still do a show on Tuesdays and Thursdays every single week. And we have a couple other live programs going on outside of our regular Echo Live programming. Today at 5 o'clock, we are having a live STEManista interview with some of our STEManista role models and ambassadors to some of our various programs. This will be a live interview that takes place on Facebook and YouTube Live. We hope you tune in. You can ask questions to some of our STEManista role models about their career in science and what they are most excited to share with you. And of course, I mentioned last week during our Global Soundscapes or Soundscape Bingo game that we are hosting our free Echo Live Movie Day, our first free Echo Live Movie Day on Wednesday, August 12th. So that is next Wednesday from 1 to 2 o'clock Eastern. It is free. Anyone can join in, but if you would like the Zoom connection information, because this one will not be on Facebook or YouTube Live, if you would like the connection information to join us in Zoom that day for a free complete show of Global Soundscapes, which is an interactive show, you just need to fill out the registration link that we posted with our video last week. You can find that information on the Michigan Science Center website, on our Facebook, on our YouTube channel, and I hope that I will see you all there. Of course, we'll be back here on Thursday as well with more Echo Live. Paulette will be here for another very exciting virtual planetarium show. So hopefully that answered your question out there, Evan. Paulette will be here on Thursday for another virtual planetarium show where we're going to talk about the Perseids meteor shower that's actually happening right now. So Paulette's going to talk to us about what comets and meteors are. She's going to tell us how we can get an up-close view of the Perseids as they fly over before they peak on August 12th, I believe it is. So you won't want to miss this show because it's going to teach you some very important skills about astronomy and observation that we haven't talked about so far. So with that, thank you everyone so much for joining us. I've had a fantastic time seeing you guys all today. I'll see you back here on Thursday for more Echo Live. Have a